All right. Um, so, oops. Assignment 6 to do today, 5 o'clock. And I will have solutions posted afterwards. Final exam next Wednesday, so a week from today. And assignment 7 due on Tuesday. Again, get started on that today if you haven't already, and send me initial ideas, or initial solutions you have in PDF format, please. And I can take a look at those for you, help you out. And I'll make sure over the weekend to be available on email to do that. All right. Final questions on assignment 6. Okay. So back to chapter 7. So remember that this r bigger than or equal to 0 here, that denotes the non-negative real numbers. All positive real numbers, including 0. And then a metric space is a set M, along with the distance function, also called a metric, D, from M cross M to R bigger than or equal to 0, satisfying the following. The distance from X to X is always 0. If X is not equal to Y, then the distance from X to Y is positive. Distance from X to Y is the same as the distance from Y to X, symmetry condition, and then the triangle inequality. Distance from X to Y plus the distance from Y to Z is bigger than or equal to the distance from just X to Z by itself. And this is the picture to, think of. So the most basic example of a metric space is just the real numbers themselves, in which the distance from X to Y is absolute value of X minus Y. So the length of this segment along a number line. So the whole notion of, distance along a ruler. And then in the two-dimensional plane, R cross R, we went over 3 different types of metric spaces that you can get. So there's the metric space in which distance is, given by the distance formula, the Euclidean metric. In other words, the Pythagorean theorem. Distance in the taxicab metric, and this thing that we'll call the max metric. So, for example, in the xy plane, here's the point 1, 0, and here's the point 3, 5. The Euclidean distance between those points is the length of this segment, which is square root 29. The taxicab distance is this right here, 2 plus 5. And the max metric distance is just 5. So, most generally, in general, the max metric distance is less than or equal to the Euclidean distance is less than or equal to the taxicab distance. So, you know, traveling along a taxicab route is the slowest way of getting from A to Z in terms of these three metrics. Other examples of metric spaces, right? The sphere, the surface of a sphere, of some constant radius, and the distance from x to y is this distance along a great circle. So given any 2 points on a sphere, maybe you're not aware of this geometry, maybe you are, but given any 2 points on a sphere, there is a unique great circle which goes through those 2 points. Unique, great circle, which is a circle that cuts the sphere into 2 equal hemispheres. So like the equator is a great circle, and then any longitudinal line through north and south poles, those are all great circles as well. But, you know, besides those, any 2 points that you have on a circle, or on a sphere, there's a unique great circle that goes between them. Think about it. You know, take 2 points on a sphere and draw a circle on the sphere that goes through both of those points, and you can sort of slide that circle around, right? And the distance becomes the smallest once you've slid that circle, you know, around the back of the sphere. So that's how you get shortest distance between 2 points on a sphere. And you know, there's ways you can measure that distance as well. There's little formulas that give you that. I mean, they're complicated, but you know, but they're there. Another metric space, you know, things get really like different with metric spaces. They're not all, you know, these aren't all your father's metric spaces. These, you know, they get really sort of exotic. And for example, there's this metric space M where f of x it's a set of all f of x where f of x is a continuous function, but not a point. It's a continuous real valued function on the interval from 0 to 1. And the distance between 2 functions is the integral of the absolute value, like that. This metric space is actually called L1. Right. Then there's other ones. There's L2, which is the same set, or well, LP, which is the same set where the distance from f to g is the integral from 0 to 1 of, how does it go? Fx to the p minus 8. Oh, you know, I'm forgetting. I think it's fx minus gx to the p dx, and I take the square root of p at the end. Yeah, the pth root, not square root, the pth root, something like that. Anyway, these are very interesting metric spaces, and that's like a whole area of mathematics on its own. Functional analysis is the study of these metric spaces. We're not going to talk about them, but just, you know, just so you can see it. All right. So, in other words, you know, metric spaces are varied things. Please don't think of it as something you can impose assumptions upon. Okay. The only facts you know about a metric space off the top of your head are these facts here. And then there are other facts that, you know, we're going to establish. It satisfies 4 properties, 1, 2, 3, 4. That's it. Okay. You can't add things in metric spaces. You can't take x and y in M and add them. You can't do that. Okay. There's no algebraic structure. You can't multiply them. You can't subtract them. You can't take their exponents. None of that. No algebraic structure. You just have these 4 properties. Okay. One of the most important objects in a metric space is called these are called open balls. So given a metric space M, x in M, and a real number, positive real number, the open ball of radius r centered at x is, well, you denote it this way, BR of x. It's the set of all y in the metric space such that the distance from x to y is less than r. So that's the ball of radius r around x. So for examples, in r cross r, in the xy plane, the open ball around xy in the taxicab metric looks like this. All right, here's xy, x plus ry, xy plus r, and then subtracting r from x and y. So you have this diamond here. In the Euclidean metric, the ball of radius r around xy is, the disk, circle, not including the boundary. That's why I have that dashed line. And then in the max metric, the ball radius r around xy is this big square here. So you'll notice that, here's the taxicab metric ball. And here's the taxicab metrics ball.
Why is it still called a ball if it's a square?
Because the intuition is always the Euclidean metric. The intuition is the Euclidean metric. Intuition and, what it is are two different things. R cross R with the standard Euclidean metric, this should be what your intuition is working with. Although your proof cannot be by intuition. Y'all getting what I'm saying? This is the intuition, but don't think you can do anything in a metric space other than those four properties and things that we're gonna, conclude from those four properties, prove from those four properties. Okay, but I mean, if you want to think of a metric space just as being this, that'll get you pretty far. It won't get you everywhere, but it'll get you pretty far. Okay, in this course, it'll get you all you need. All right. So the balls of radius r of these various three metric spaces on the same set with different metrics, like the taxicab metrics ball is this, the Euclidean metrics ball is that, and the max metrics ball is this. And then there's other metrics whose balls are like that. So it's this whole spectrum of metrics. So for this time, let M be a metric space, and let X and Y be distinct elements of this metric space. Okay, show that there are open balls around X and Y that are disjoint. You can always put open balls around X and Y, as long as they're different, that don't overlap. Okay, so let's give a proof of that. Now, when you're defining open balls, okay, you have to describe the radius in terms of, like, when you're defining a ball, that's got a specific radius, you have to say what that radius is. Okay, so we need to display R and S. Tell me what R and S are. As actual numbers, and then show that those balls are disjoint. Okay, so anybody think about this? What we can use to define R and S? There's only one number we know that we're working with at this point, and it's not R and it's not S because we haven't defined those yet. There's only one number in this example that's a known fixed quantity. And that number is the distance from X to Y. So here it goes. Okay, because X is not equal to Y, the distance from X to Y is what? Is what?
Is it y minus x?
That's just in the real numbers. All right, you can't add and subtract things in metric spaces. So, going back to the 4 properties of metric spaces. This is all you can say. You can't add x and y. You can't.
It's equal to the distance of yx.
Right, which is what? Was anything special about that? Because x and y are different? What's special about that?
It's greater than 0.
That's it. That's all we know. Period. Is greater than 0. So now let r and s actually be the same number, be equal to the distance from x to y over 2. So distance from x to y, that's the only number that's actually known, fixed number that we're working with here. Now we need to define r and s in terms of that fixed number. Okay, so just half. Or a third, if you want. Or a quarter. And anything will work. As long as you go with 1/2. All right, so let us now show that. So here's the intuitive picture. So like here's x, and here's y, and here's the distance from x to y. So the distance from x to y is a straight line, right? In a metric space. Right? It always looks like that in every metric space. The distance from x to y. The metric space is a 2-dimensional flat plane, and the distance from x to y is a straight line. Right? All metric spaces are that. Yes? Correct? Or incorrect? Correct or incorrect? Correct or incorrect? Guys, you all there? It always looks like this, what I'm drawing here, right? Every metric space looks the same, right? Well, obviously the answer is no, right?
No.
No. But this is the intuition you should be using. But your proof cannot, cite the intuitive picture. It can illustrate what you're talking about and guide what you write, and that's all wonderful. In that case, a picture is worth 1,000 words, as we said. Okay, but the proof can, has to be completely formal from the axioms, the 4 properties of metric spaces. Okay, so now let's show that. So I mean, here you can see that that the distance, 1/2 the distance. It looks like they overlap, but they actually don't. If you want, you can make it like the distance from x to y over 3, in which case they won't over, they don't even look like they overlap. I mean, it's just that, the boundary of these balls actually is not part of the ball. So now let's show that the ball of radius around x intersect the ball of, was it x and y, or was it u and v? X and y. Is empty. So let's show that those, so we've defined it, but it doesn't say that it's empty, right? We've defined R and S, now we have to show that they're empty. I claim they're empty, okay, but we have to actually show that. All right, how would we show that? Well, normally one does not work with the empty set or prove that a set is empty directly. Normally this is something done by contradiction, right? Because to prove that I mean, I don't know, you can, but I mean, this is one of those things where a contradiction proof is just natural because it gives you something to work with. So, by way of contradiction, assume that the balls do overlap. All right, that means what? What does that mean? What exists? What exists if the intersection of these two sets is non-empty?
Is a subset.
It's a subset with something in it. Right? There is some z in the intersection of those two sets. Okay. Well, now, right, by the definition of open balls, right, the distance from x to z is what? Less than the radius. What's that radius?
The distance from x to y divided by 2.
Distance from x to y over 2. And the distance from y to z, or z to y, do it this way, is again less than the radius, which is the same. Therefore, right, the distance, by the triangle inequality, the distance from x to y is less than or equal to the distance from x to z plus the distance from z to y. Right? That's the triangle inequality. So, intuitive pictures, right? So here's x, here's y, here's z, and z is somehow supposed to be in the intersection of both balls. So the distance from z to the center of each ball is less than the radius, which is dxy over 2, right? But this is less than dxy over 2, and this one is less than dxy over 2, which is equal to dxy. Therefore, what? What does this give us? What does this whole thing give us here? All right, so I'm working with a string of inequalities all pointing to the left. So I have that the first thing is strictly less than the last thing. This is what?
Equal.
Well, no, I concluded that the distance from x to y is strictly less than the distance from x to y. That is
A contradiction.
contradiction. So that's it. So, right, I mean, we want to show that that those two balls were disjoint. So I assumed that they weren't. And by assuming that they weren't, I was able to reach a contradiction using the triangle inequality. Okay. Assignment number 7, problem number 1. Here, no, not problem number 1, excuse me. Problem number 2. Uses ideas like this. Problem number 2 uses ideas like this. You have some open balls, okay? You have the open ball of radius r around u, and you have the open ball of radius s around v. Okay, open ball around u, open ball around v. So now r and s are given. They're given things. Let M be a metric space, and these guys are open balls. Okay, so you're given these things. And assume that their intersection is non-empty, that there is something inside there. All right, so there's some z. There's an element z in the intersection of those two balls. Use that element z and the triangle inequality to show that the distance from x to y, or sorry, from u to v, is less than r plus s. And, use triangle inequality again to show that the distance from A to B, where A is an element of the ball around U and B is the element of the ball around V, that show the distance from A to B is less than 2R plus 2S. Okay, same ideas like we just did here. So, okay, go over this proof. Do this proof on your own, without looking at this stuff. Do that proof on your own, compare what you got to what I got. If not, go over it again, understand this proof, and then once you do that, this should be pretty simple. Number 2, same kinds of ideas, not the exact same ideas, but same techniques will be used. Okay. All right. Sequences. So some notation first of all. Definition, I guess. Okay. So a sequence is a just list of elements in a metric space M.
That have a ordering.
Yeah. No ordering in metric space. You can't compare things in metric spaces. Like, can't add them, you can't subtract them, can't multiply them, can't say one is less than the other. None of that stuff. No algebraic structure at all. Now, metric spaces that you study will have algebraic structures, specific ones, but in general they don't. So a sequence in a metric space is just, is an infinite list of elements x1, x2, x3, x4, just like that. So normally we write xn to denote the sequence. So the same kind of notation that was used in calculus 2. xn to denote the sequence in its entirety. Okay, but we will also use xn to denote like the nth element of the sequence. of the sequence. So we use xn to denote the whole list. Well, all the elements of the sequence at one time. But you can also use xn or some other subscript to denote the nth element of the sequence when n is some fixed quantity. Right, so n can be variable or n can be fixed. Right, fixed, but we don't know what it is. Fixed but unknown. Okay, so that's a sequence. So for example, so in just an R, right, with the usual distance, metric, x n equal to, say, -1 to the n is the sequence. -1, 1, -1, 1, -1, 1, so on and so forth. All right, x n equal to 1 over n is the sequence. 1, 1/2, 1/3, 1/4, a harmonic sequence. So on and so forth. No series, just sequence. All right. Now, what we can talk about with sequences, even though we don't have any algebra in a metric space, we can talk about convergence, because convergence only relies on distance. Okay, so we write xn converges to L, to xn arrow L, to mean sequence xn converges to limit L. All right, the formal definition is as follows. Is xn converges to L when there is natural number capital N, when for every r bigger than 0, there is a natural number n such that the nth element of the sequence and the n plus first element of the sequence and the n plus second element of the sequence, what am I doing? xn plus 1, xn plus 2, xn plus 3. So at some point, the sequence gets stuck inside the ball of radius r around L. No matter how tiny that radius is. Yeah, that's the formal definition of convergence. So, like all throughout your calculus courses, your teacher may have said what the formal definition is, of a function, the limit as x approaches a of some function f of x is equal to L. This is a simpler thing about that, sequences. You may be given the formal definition, maybe not, but you have an intuitive idea of what it means. It means that the elements of the sequence, they get closer and closer to the L, right? You get closer and closer to L, and they never go away from L. Just keep getting closer to L and don't go away. Well, what does that mean? For every closer means as close as you want. So for every measure of closeness, for every real number r bigger than 0, no matter how tiny, at some point, the sequence gets stuck in the ball around L. All right, so here's the intuitive picture. So here's L. Here's the ball of radius r around L. So there's the ball of radius r around L. Here's the sequence: x1, x2, x3, x4, blah, 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 xn minus 1. But then suddenly, we're inside here, xn. xn plus 1. It's kind of too big here. xn plus 2. You know, at some point, you're going to get stuck inside that ball. All right, so you got x1, x2, x3, x4, you know, blah, 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 xn minus 1, and then bing, you get stuck in the ball. xn plus 1, xn plus 2. Not that you weren't in there before. I mean, maybe x20 is here, but then x21 comes back out or something like that. That's fine. You can go in, out, in, out, in, out that ball of radius r around L, but at some point, you get stuck, okay, inside that ball. So another way to say this is for every r bigger than 0, there is n in the natural numbers, such that for every bigger than or equal to n, the distance from xm to L is less than r. Right. The distance, it, you know, at some point just becomes small and stays small. Where small is some really tiny, tiny, tiny number for r, as tiny as you'd like it to be. Okay, so we can talk about this notion of limits, you know, sequences and limits in a metric space because we have distance. No need for any algebraic structure whatsoever. So let's do an example. So in the real numbers, just the plain old real numbers, with, you know, the distance from x to y being equal to x minus y. Okay, consider the sequence uh, 1 over n. So let's prove that. One over n converges to, well, what do you think it does? Converges to 0. Okay. I'm sorry, guys. I'm gonna have to excuse myself just for one minute. All right. So consider that sequence 1 over n. Let's prove 1 over n converges to 0. Limit 0. So we have to prove the following. For every r bigger than 0. To prove something for every r bigger than 0, you have to start with any arbitrary r bigger than 0. So you just say let r be bigger than 0. Let r be bigger than 0. Okay, you don't know anything about r. It's just some positive real number. Intuitively, it's something really small. Okay, 0.000001, whatever it might be. Okay, now, given r, I gotta have this specific number n. Right? That n is gonna have to be in terms of r, however. Right? For every r, there exists an n. Right? For every student, there exists a name by which he or she is called. Right? But that name is dependent upon the person. right? So, you know, your name is Rick, your name is Martha, you know, whatever it is. That name depends on the person, right? So here, that natural number depends on the R. So it's going to be in terms of R. Right? When you say depends on R, it's in terms of R. So let R be bigger than 0. Pick any natural number n that is greater than 1 over R. Right? R is really tiny, so 1 over R is really what? Really what?
Smaller.
Big.
Big. Yeah, so R is like, you know, 10 to the negative 20 or something like that. Then 1 over R is 10 to the 20. Right? You know, 1 septillion or whatever the number is supposed to be called.
The smaller the denominator, the huger the number.
Right, exactly. Yeah. The huger the reciprocal. Yeah. Right. Yeah. Sorry, you said it right. I said it wrong. So let n be any natural number bigger than r. So now, right, for any m that's bigger than or equal to n, right, the distance from 1 over m, the element of the sequence, to the limit 0, well, which is equal to the absolute value of 1 over m minus 0, which is equal to just 1 over m, right, is less than 1 over, or less than or equal to 1 over n, which is less than r. Right? So like if r is 10 to the negative 20, then, you know, or something smaller than 10 to the negative 20. Yeah, if r is 10 to the negative 20 or some I guess bigger, slightly smaller than that, then at 10 to the positive 20, the sequence gets stuck in the ball of radius r around 0. Right? The distance from the sequence, 1 over m, to the limit, 0, which in this metric space looks like this, is equal to 1 over m, is less than or equal to 1 over n, which is less than r, right? 1 over m is less than or equal to 1 over m because m is bigger than n, right? When you take reciprocals, the inequality just gets flipped around. Right, and then, so 1 over n is less than r itself. So there's the formal proof that 1 over x goes to 0, as, you know, we've been thinking for, you know, ever since you looked at the graph of the function 1 over x. Here's another example. So, in problem number 1 on the homework, okay, in problem number 1 on assignment 7, okay, you will prove the following. Okay, if M is a metric space with distance function d sub m, and n is a metric space with distance function d sub n, I guess I should use capital M and n. Alright, so M is a metric space with distance function dm, n is a metric space with distance function dn, then M cross n is a metric space with distance function d defined by the distance from xy in Mn to AB in Mn is equal to the distance in M from X to A plus the distance in N from Y to B. Okay, so that on assignment 7, that's number 1. Right, so given two metric spaces, you can take the Cartesian product of those two metric spaces and define a metric this way by just adding up the metrics of the previous vector spaces. So, for example, like the two-dimensional plane with the taxicab metric, the two-dimensional plane of the taxicab metric is that's the metric that takes the metric space on the real numbers, on the real number line, with just that ordinary ruler metric, and taking the Cartesian product, right? Where's the example? All right, so in R, the distance from X to Y is just this ruler metric thing here. Right, and then in R cross R, the taxicab metric, the distance from XY to AB is the distance from X to A in the real numbers, plus the distance from Y to B in the real numbers. So that's the taxicab metric. It's done, in the way that problem number 1 is describing. It's done in the way that problem 1 is describing the way you do it with general metric spaces. Okay, so given two metric spaces, you can take their Cartesian product this way and get another metric space. Right, so as before with Cartesian products, you have to break down the question of, does the Cartesian product satisfy the 4 properties of a metric space by breaking it down into a question of, its components. What's happening in Dm, in metric space M, and what's happening in metric space N. So just like we've been doing with relations, working with Cartesian products that way. So that's problem number 1, okay? But let's assume that's true now. All right, so let's assume this is true. Okay, now, say that sequence xn converges to L in metric space M, and sequence yn converges to K in metric space N. Show that sequence xn yn converges to L comma K in M cross N. So I got a sequence in M, a sequence in N, and we can therefore get a sequence in M cross N and show that the limit of that sequence is the, pair of limits for the original sequences. Okay, so let me just do this quickly in the last bit here. So let R be bigger than 0. Let R be bigger than 0 because xn converges to L in M. There is a natural number. So natural, I don't want to use capital N. There is a natural number. So there's natural number R in N such that for every M bigger than or equal to R, the distance from xm to L is less than, not R, but R over 2. Because R is bigger than 0, so is R over 2. And then because, so let's call it R1, I guess. And then because x or y n converges to k in n, there is R2 in the set of natural numbers, such that for every m bigger than or equal to R2, the distance from ym to k is less than r over 2 again. So now, let r be equal to the larger of R1 and R2. Whichever one's bigger. You got these two natural numbers, R1 and R2. Let R be the bigger one of the two. Or if they're the same, then let it be equal to both. So now if m is bigger than R, if m is bigger than or equal to R, then m is bigger than or equal to R1 and m is bigger than or equal to R2. Therefore, the distance of xm, ym to the point LK is equal to, by definition, of D. Well, it's the distance in m from xm to L, plus the distance in n from ym to L, or K. Right? But this one was less than R over 2. This one was less than R over 2. So that's equal to R. So the distance from xm, ym to LK is less than R. As required. Right? For every R bigger than 0, right? So we picked an R bigger than 0. I showed that there is a natural number, capital R, such that every point in the sequence, xm, ym, where m is bigger than R, is distance less than little r from LK. So the sequence got stuck in that ball there. Okay, so this first problem on sequences. The homework assignment has got this problem on sequences. This is kind of like, oh, that should be strictly less than. Number 3, I'll change that. It's supposed to be strictly less than. Number 3 is I use similar techniques to what we just did. Essentially, it uses this half of R business. Okay, so it uses this half of R business. So you know, we've already covered enough material to get through problems 1, 2, and 3. All right, so next time, questions on this. Okay, so be prepared with questions, and we'll talk about those. All right, and actually, I think we've actually got enough for number 4 too. Yeah, there's enough for number 4. Enough stuff for number 4. Okay. All right, guys. Have a good day, and we'll see you on Friday.